Hello everyone, welcome back to the channel. For this session, we're going to look at the determination of natural frequency and mode shape. So there are various ways that we can get the natural frequency by using some approximation method, like standard matrix iteration method, Dunkerly formula, Rayleigh's method, and Holz's method. So for this session, I'm going to cover two approaches, which are the standard matrix iteration method and Dunkerly formula. So let's look at the standard matrix iteration method. Alright, so a general equation of motion, something like this, whereby you have the mass matrix and the stiffness matrix. And when you assume the harmonic motion, you will get the equation will be transformed into this. So negative omega squared mass matrix multiplied by x matrix x plus stiffness matrix equals to 0. So this is after we have assumed the harmonic motion, right? So in order to use matrix iteration method, there are two possible solutions that you will get. One is that it will converge to the lowest natural frequency, and another one, it will converge to the highest natural frequency. So using standard matrix iteration method, you will get either the lowest natural frequency, or sometimes we call it as fundamental natural frequency. And the second one, you can also obtain the highest natural frequency. So in order to get the fundamental or the lowest natural frequency, you need to multiply this equation with the inverse stiffness matrix. Right? So basically, when you multiply this equation with the inverse stiffness matrix, you will get your lowest natural frequency. But if you multiply this equation with inverse mass matrix, you will obtain the highest natural frequency. Right? It is pretty easy. Right? Now let's jump to the solution or an example. So in order for you to get the lowest natural frequency, as I have mentioned earlier, you need to multiply it with the inverse stiffness matrix. So these are the solution procedures, or sometimes you call it as standard operation procedure, in order for you to get the lowest natural frequency. First, you need to identify the matrix K and matrix M. Second, you need to calculate the K inverse. You can use your calculator for this. Third, define the initial trial vector. And then next, you're going to multiply the K inverse matrix with the mass matrix, and you will get the X nu. And then you normalize the results, whereby you divide your X nu with the largest X nu. And once your calculation has converged, you will use the new trial of X, and then when it is converged, in order for you to get the lowest natural frequency, you can use this equation whereby omega n is equal to square root 1 over x normalized. So let's jump to an example. Right, before I jump to an example, this is the solution procedure for you to obtain the lowest natural frequency. If you want to get the highest natural frequency, you only need to change this into M inverse, and then you multiply M inverse with your stiffness matrix, and you just follow everything. But in order for you to get the highest natural frequency, the formula is omega squared x is equals to the x normalized. Alright, let's look at one example. Alright, the example asks you to determine the fundamental or the lowest natural frequency, given that K1, K2, K3, M1 and M2, and the trial vector is minus 2.1 and 0.9, and it asks you to stop your calculation at the 6th iteration. So how are we going to perform this? Remember that you can always follow to the solution procedure for the lowest natural frequency. Alright, first you need to identify matrix K and M, calculate K inverse, and so on. So from this, basically, first thing that you need to do is that you need to determine or identify the stiffness matrix K and the mass matrix M. So from here, what you need to do is you need to draw the free body diagram, and then you need to do your equation of motion, and then from there you can determine your mass matrix and your K matrix. So I'm not going to show you how. Right, so basically once you have performed your free body diagram and equation of motion, you get something like this. Alright, so let's refer to the first step. You need to identify matrix K and matrix M. So from this equation of motion, so your matrix K is 30 minus 20 minus 20, 35. Okay, you need to do it yourself in order for you to understand. And the mass matrix M is 1.2002.7. Right, the second step is that you need to calculate the inverse K stiffness. So by using your calculator, again, I'm not going to show this to you. I assume all of you know how to use your calculator well. So you will get 0.054, 0.031, 0.031, and 0.046. And then the third procedure is that you need to determine your initial trial vector. So it's already been given in the example that you need to use initial trial vector of minus 2.1 and 0.9. And then the fourth step, because we want to determine the fundamental or the lowest natural frequency, so you need to multiply K inverse multiplied by mass matrix multiplied by initial trial vector, and you will get your new trial vector. Alright, so in order for you to be easy, in your calculator you can put this as matrix A, this as matrix B, and this is matrix C. So next you need to perform your iteration. I prefer for you to use a table, okay, in order for you to see it more clearly. So this is your x new. How you're going to get your x new is basically matrix A multiplied by matrix B multiplied by matrix C in your calculator. And then this is your x new divided by largest x new. And then this is the x normalized. Alright, so once you have input your matrix A, matrix B, and matrix C in your calculator, you can start to fill up the table. So for the first iteration, I put everything in my calculator. So I will get the new x new as negative 0.061, 0.034. So the next column, if you see x new divide by largest x new. So from here, the largest x new is this, because this one is negative, so the largest is this. So you can write it as 1 over 0.034 multiplied by 0.061, 0.034. And then when you calculate these, you will get your x normalized, which is negative 1.794 and 1. Okay, you need to do this yourself or else you won't understand. So once you have completed this, so this will basically be your new matrix C that you need to put in your calculator, which is in this one. Okay, A and B remain the same, but the C you need to refer to your new x normalized. So then do the iteration again, because the question asks us to stop at the 6th iteration. So for the second iteration, once I multiply matrix A multiplied by matrix B and matrix C, we'll get negative 0.033 and 0.057 x. Okay, so if you look here, this is now your new largest x new. So x new divided by largest x new is 0.057 multiplied by negative 0.033, 0.057, and then your new x normalized would be negative 0.579 and 1. So now this has become your new C, and you need to put back in your calculator. Then you perform the third iteration. I think some of you have learned this in the engineering maths 4, so I assume this is not something new. So the third iteration, my x new would be 0.103, and then this is the largest, so 0.103, 0.046, 0.103, and then my new x normalized would be 0.447 and 1. So we can't stop yet because it asks us to stop at the 6th iteration. So the 4th iteration, you will get 0.113, 0.141, so 1 over 0.141, 0.113, 0.141, and your new x normalized would be 0.801 and 1. Fifth iteration, you will get 0.136, 0.154, 1 over 0.154, 0.136, 0.154, and your new x normalized would be 0.883 and 1. So for the final iteration, because it asks us to stop at the 6th iteration, so I will get 0.141 and 0.157. So once you have performed your iteration, okay, and then the next step is that when converge, so the equation for the lowest natural frequency is square root 1 over x normalized. So if you refer back, x normalized, so basically it is your final largest x nu, which is this one. Okay, so equals to square root 1 over 0.157, and you will get the answer of 2.524 radian per second. Alright, so if the question asks you to get the answer in hertz, so in hertz, basically you just need to convert. So natural frequency in hertz is 1 over 2 pi omega n, which is 0.402 hertz. So it's pretty easy, it's not that hard. So I recommend for you to do yourself example 1 and also example 2. So what I've shown you just now is how you get lowest or fundamental natural frequency by using matrix iteration method. So again, if you refer to the lecture notes, in order for you to get the lowest natural frequency, you need to multiply with K inverse. But if you want to get the highest natural frequency, you need to multiply it with M inverse. So that's all for the standard matrix iteration method. Alright, now let's look at the second approach, which is the Dunkerly formula. Alright, so basically Dunkerly formula, you can only get the fundamental or lowest natural frequency. In the matrix iteration method, you can get either highest natural frequency or lowest natural frequency. But using Dunkerly formula, you can only get the fundamental or the lowest natural frequency. So to cut it short, basically it's pretty simple, Dunkerly formula. In order for you to get the lowest natural frequency using Dunkerly formula, you just need to refer to this equation. 1 over omega I squared is approximately A11 M1 plus A22 M2 plus ... plus ANN MN. Alright. So let's look at the example. Alright, I know some of you are quite blur how to use this one. So let's look at example 3. Predict the fundamental natural frequency using Dunkerly method. So it is quite the same with the previous example. Alright, the values are all the same. Okay. So now if you look back in here, what you need to determine is that A11, M1, A22, M2, and so on. So from this question, which is the same as the previous example, so Dunkerly method, please remember that Dunkerly method you can get the lowest natural frequency. So it is based on this approximation A11M1 plus A22M2 plus dot 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 plus ANNMN. Alright, so from the previous example, okay, you get the equation of motion 0.20, 2.7, x double dot 1, x double dot 2, plus 30 minus 20, minus 20, 35, x1, x2 equals to 0. So in order for you to get the lowest natural frequency using the Dunkerly method, you need to identify what is A11, M1, A22, M22, and so on. So since this is a 2 by 2 matrix, so you only need to identify up to these 4 parameters. So what is A11? Okay, if you look back at the lecture notes, okay, so matrix A is actually the K inverse matrix. Okay, so once you put all of the values, so this is your K matrix. We know that K inverse is our matrix A, and K inverse, if you put your matrix K in your calculator, you will get 0 0.054, 0 0.031, 0 0.031, and 0 0.046. So A11 is actually this one. Okay, I assume all of you know the coordination in a matrix, and M1 is actually this one. Okay, or you can also refer back to the question. I already give you what is M1, what is M2. So next is A22. So this is A22, and M2 you can either refer in from here or refer back from the question. So we have completed all of the unknown. In order for us to get the lowest natural frequency, so using Dunkerly, 1 over omega I squared is approximate to 0 0.054, which is A11, and M1 is 1.2, plus A22, which is 0 0.046, multiplied by 2.7, and you will get the answer of 0.189. Okay, so remember this is 1 over omega squared. Okay, so in order for you to get the omega I, it is the square root of 1 over 0.189, and then you will get the answer of 2.3 radian per second. So this is the lowest or the fundamental natural frequency using Dunkerly method. So if you compare using Dunkerly, you get 2.3 radian per second, the lowest natural frequency. And if we use matrix iteration method, you will get 2.524 radian per second. So there are differences, okay, but generally using matrix iteration method, you will get more accurate result compared to Dunkerly method, because Dunkerly method is just a simple assumption. It's pretty easy, right? It's quite straightforward, but it's just a simple assumption. Right. So if let's say you're using the matrix iteration method, the more you iterate, okay, the more you iterate, the accurate the answer would be. Okay. So in order for you to get accurate result, you need to iterate more. Okay. But again, if you refer back to the question, always read the question whether it asks you to stop at the fourth iteration, fifth iteration, sixth iteration, and so on. All right, so that's all for this session. All right, I hope all of you can see how simple that we can approximate the natural frequency using approximation method. So see you again next time. Thank you.